Have you ever really stopped to think about energy? I mean, not like some dry chapter in a textbook, but as this secret force that makes literally everything happen. It's the story behind what makes things go, what makes them stop, and what makes them change. Today, we're going to pull back that curtain and take a look at its secret life.
Okay, just look at this thing. This is one of the tallest, fastest roller coasters on the planet. We're talking over 42 meters high. A super powerful motor has to launch these cars all the way to the top before they just fly down the tracks at insane speeds. That's a whole lot of energy packed into one ride. But have you ever wondered, what does it actually take to make something like that move?
And that really leads to the big question, right? To get something so huge moving so fast, where does all that energy actually come from? And where does it go when the ride is over?
Well, the answer to all of that lies in the basics of energy itself, this invisible power that basically runs the entire universe.
All right, probably the best way to get a grip on this whole concept is with a simple analogy. Just think of energy like money. The total amount of money in the world is fixed. It doesn't just appear out of nowhere, right? It has to be stored somewhere, and it can be transferred around.
So just like you have different bank accounts, maybe a savings account here, a checking account there, energy is held in different places. Physicists call these stores. The total amount of money stays the same. It just moves between your accounts. Well, energy works exactly the same way.
So let's take a peek inside these different energy accounts, or as we should really be calling them, these energy stores.
In our physics bank, there are pretty much 6-man accounts. You've got the kinetic store, that's for movement. Gravitational potential, which is all about height. Elastic potential, for anything stretched or squashed. Chemical potential, that's the energy in stuff like food or batteries. Internal, which is basically heat. And finally, nuclear, which is the incredible energy locked right inside atoms.
And the cool thing is, you can see these stores all around you, every single day. Look at these examples here. That spinning frisbee, it's got energy in its kinetic store. The stretched rubber band is just full of elastic potential energy. The food on that plate is a classic chemical store, and that book sitting up on the shelf has gravitational potential energy. It is literally everywhere.
Okay, so we know where energy is kept, but how does it move from one store to another? I mean, how does the chemical energy from your breakfast become the kinetic energy of you running for the bus? Well, that whole process is called an energy transfer. An energy transfer is really simple. It's just the process of moving energy from one account or one store into another one. It's like sending money from your savings account over to your checking account. That's it.
Let's look at a super simple example. When you push a cart, the force you apply over a certain distance, that's called doing work. And that work you're doing is a mechanical energy transfer. You're taking energy from the chemical store in your muscles, and you're transferring it into the cart.
And what's really cool is that we can actually see this transfer happen. Check out the bar on the left. Before the push, the cart has a little bit of kinetic energy. But after the push, look at the bar on the right. The mechanical work has transferred energy into the cart's kinetic store, and its energy has clearly gone up. The energy has moved. Okay, now we get to the most important part of this entire story. In this whole universe of energy stores and transfers, there is one single totally unbreakable rule that governs everything. And here it is, the principle of conservation of energy. It basically says that energy can't be made from nothing, and it can't just vanish into thin air. The total amount of energy in a closed system is always constant. It just changes form. A perfect frictionless pendulum is the classic example of this. At the very top of its swing, all its energy is sitting in the gravitational potential store. As it swings down, that GPE gets transferred into the kinetic store, and it's moving fastest at the bottom. Then, as it swings back up the other side, that kinetic energy gets transferred right back into GPE again. But wait a second. If energy is conserved, why does a real-world pendulum eventually stop swinging? I mean, if the energy isn't being destroyed, where on earth does it go? And here is the crucial bit. The energy isn't lost. As that pendulum swings, things like friction and air resistance are transferring some of that energy into the internal stores of the pendulum and the air around it, basically heating them up just a tiny bit. The total energy is the same, it's just that some of it has dissipated into a less useful form.
This idea that some energy always dissipates or gets wasted is so important for understanding how we use it in the real world. And that brings us to two really practical concepts: power and efficiency.
Power is all about speed. It's not just about how much energy you use, but how quickly you use it. The faster you transfer energy, the more powerful you are. And we measure that in watts.
So let's put a number to this, right? Imagine a student, let's call him Eugene, runs up a flight of stairs. In doing so, he transfers 900 joules of energy. If he does it in 5 seconds, his power output is 180 watts. Now, if he did that exact same run in half the time, he'd be twice as powerful. Simple as that.
Now, since some energy is always transferred to non-useful stores, we need to talk about efficiency. Efficiency is just a percentage that tells us how good a machine or a process is at putting energy where we actually want it to go.
Take your typical power station. For every 100 units of chemical energy you put in from the fuel, a whopping 55 of those units are dissipated as heat to the surroundings. Only 45 units actually become the useful electrical energy we want. So that means its efficiency is only 45%. Which brings us right back to the beginning. We know energy can't be created or destroyed. It only gets moved from one store to another. And we know that in every single transfer, some of that energy is going to be moved to a less useful store. So the big question isn't how do we make energy,
But rather, how will we manage these transfers efficiently and sustainably to power our future? You know, understanding these fundamental rules of the game is really the first step to answering one of the most important questions our entire world faces.